Hello everyone, my name is Dan Andre Anton. I'm the founder of Unleashed Engineering, which is a spin-off project from Automotive Consulting in partnership with GNS. At Unleashed Engineering, our goal is to streamline the R&D of smart tires for electric vehicles. This presentation is about the evolution of tire modeling requirements. Therefore, I will start with the history of 3D Abacus FEA tire modeling approaches, highlighting the challenges in the legacy model creation processes with concrete customer examples. Then I will touch on the standard investigations, showcasing examples of an upgraded modeling approach for static and dynamic use cases. We will enter the new case automotive context as we move forward, highlighting the need for beyond standard investigations. Next, we will look at a couple of innovative use cases, starting from smart tires today and moving to super smart tires in the future. By the end of the presentation, we will analyze some field outputs and delve into historical data to find valuable insights. Finally, I will summarize our findings, emphasizing the importance of these advancements in tire and beyond tire technologies applications. Before getting into the technical aspects of this presentation, we must answer why we are having this talk. What is the context? The wheel, humanity's oldest invention, is getting smarter by integrating sensors to enhance vehicle dynamics and sustainability. According to Pirelli, the McLaren Artura was the first street car equipped with a cyber tire, essentially an innovative tire, meaning a tire with a sensor that starts the dialogue between the car and the tires. In this context, as we add sensors to tires, engineers cannot use the same trial and error approaches, like the one captured in the upper right picture, to secure the safety and performance of the new system. So our goal is to overcome the limitations of legacy tire engineering processes and help R&D stakeholders perform faster with more efficient tools and workflows. We'll cover new model creation processes and improved engineering tools to tackle new challenges. Now, if we speak about CAE, it is widely known that thanks to its capabilities, Abacus is the most advanced FEA solver used in tire engineering. In this graph, I try to capture the main evolution of Abacus solver regarding applications. Tire modeling's recent legacy belonged to the former Abacus Incorporated company, and it is estimated to have its origin in 1995-ish. Developments have been continued later by Dassault Systèmes after the acquisition of Abacus Incorporated in 2005. Capabilities like complex tire modeling using the symmetric model generation, symmetric results transfer, and steady-state transport analysis have been used in R&D organizations for many years. Also, complex material models have been developed for the Abacus solver to enable decoupled temperature displacement analysis, for instance. Without being exhaustive, this list, which I like to call top 10 scientific references, proves that Abacus is the first choice of use in FEA for premium tire makers, including for F1 tires by Pirelli. There are many more publications in the Tire Science and Technology Journal and Tire Technology International magazine, which are testimony that Abacus is used for its static, quasi-static, and dynamic capabilities in time and frequency domain. What is a bit special compared with other CA applications, like passive safety for instance, is that in the model creation workflows, like those captured in the left, the solver is involved in generating the 3D full tire model starting from a 2D axisymmetric tire model by using the SMG, SRT, and import capabilities, even when we have a dynamic or transient rolling analysis. As we will see next, these workflows cause troubles, especially for the less experienced engineers. One of the first challenges in the legacy model creation process is building the 2D axisymmetric tire models. As we can see in these two pictures in which the same 2D cross-section of the physical tire model has been built, there are some obvious issues. On the left, we see a geometric model which is simply wrong when we speak about the tire's inflated dimensions, based on a validation attempt by comparison with a scan of a real tire after inflation. On the right, we see how a good geometric model looks. The key message is that matching reality or physical tire models is possible if all tire layers gauges and total gauges align with the actual tire specification. Another challenge is building the full 3D threaded tire models with a so-called in-house developed solution. Why? The standard workflow, as I have mentioned before in the top 10 scientific references, might not have worked for this customer. So they try to build an accurate threaded tire model with all threaded features like longitudinal and lateral grooves and sipes, but they failed, as we can realize if we look closer at the mesh from the left picture. Besides bad solid elements, we noticed a mismatch between the tire's carcass and thread. On the right side is what a good 3D threaded tire model mesh should look like, without penetrations between the two main components of the tire, and by following most of the tire model cavity features and tire specification file. Setting up the correct solver input files in such a context becomes problematic. As shown in the left side, the previously presented model struggles a lot when running and eventually fails to run. Based on my overall experience, I can say that many engineers are literally fighting with such input decks, and there are obvious reasons for not trusting the in-house developed solutions for CAE and FEA. On the right side, we see that the overall number of warnings is reduced when a structured approach to building both the carcass and tire thread is used, and when an expert is involved in the model creation phase. Going further into our technical details, an upgraded 3D FEA tire modeling approach is necessary if we want an evolution of tire modeling techniques. So what is this evolution referring to? Well, it means to accurately modeling any complex 3D tire model as fast as possible, including the smallest details of the thread features, all radial grooves and all lateral grooves. A few examples show that this is possible if the right tools and workflows are used in the model creation phase. An upgraded 3D FEA tire modeling approach also means being able to model not just a tire but also different sensors that, as mentioned at the beginning, are now added to tires to enhance vehicle dynamics, like we already saw from Pirelli in the case of Cyber tire. This model is the first example of a tire system model formed by a tire and a TMS, tire mounted sensor. We notice that by adding Abacus connector elements, we can also model additional sensors like accelerometers inside the TMS. A second mounting scenario is the case of RFID sensors with antennas that can be added to the tire's sidewalls. In this case, 4 generic RFID sensors are modeled in 4 variants, each including a potential RFID tag and 2 antennas on each side of the tag. After modeling, they are embedded in 4 rubber patches, which are further attached to the sidewalls on each side of the tire. 2 different positions have been used with respect to the bit to identify the worst case for the embedding position and evaluate the impact of antennas geometries. As we can see, different element types have been used for discretization and to reproduce the physical model in the virtual world. Also, two different lengths for the springs representing the antennas have been considered, a longer length and a shorter one. So now a new question arises. Why do we need to go beyond standard investigations? The answer is quite simple. Standard is not sufficient in the current case mobility context. Usually in a tire development project, the investigation starts from analyzing the tire footprint dimensions and tire footprint mechanics, but this is just the beginning of the standard investigation, as we can see in these pictures. The contact pressure in the tire's footprint is the first variable investigated. Multiple loadings can be considered: vertical only, vertical and lateral, vertical and longitudinal, and vertical and torsional. As we can see, the FEA models capture the impact of geometry in tire footprints. Going further into answering why we need non-standard investigations, the tire spring rates are essential for a standard vehicle dynamics development project. Radial stiffness, lateral stiffness, longitudinal stiffness, and sometimes torsional stiffness are key tire characteristics for an automotive OEM. A key takeaway here should be, again, the importance of accurately capturing all tire geometry details, including the different tread grooves, longitudinal and lateral, to accurately predict a tire's response. It is valid for static and dynamic load cases scenarios, even if we only show static ones here. Without getting into further details this time, we know that these tire's responses will also significantly impact the prediction of dynamic characteristics like forces and moments, NVH characteristics, and other transient responses. We refer to a new simulation workflow built with Abacus explicit when discussing a beyond standard investigation. The current virtual testing technology, designed over 3 decades ago, does not allow testing complex tire designs, including complex threaded models with one or more sensors. The root cause is the ineffective and inefficient R&D environment, which, as described in the literature, involves the solver in the model creation phase. This not only creates a cumbersome workflow, forcing the user to manage hundreds of input and output files, but it also generates an engineering loop that is impossible to use effectively and efficiently for the development of smart tires or even super smart tires. Upgraded virtual technology is necessary to unleash the engineering potential of R&D teams dealing with these new topics. To reach an effective and efficient R&D environment, we must reduce the efforts required by virtual testing technology and multiply its results by at least a factor of 5. We can do this by eliminating the unnecessary steps from the model creation workflow and by directly building a 3D model for Abacus explicit. The natural question is whether this new simulation workflow works for a smart tire with the sensor system mounted on the inner liner. And as we can see, yes, it does work, especially when we consider the specific use cases and the application of smart tires. As we can see in these simulation videos, with various focuses, 3D perspective logs, and cross-sections in the real-time simulation, the system model works faultlessly in the first tire system model scenario. The next natural question is whether this new simulation workflow works for a smart tire with the sensors mounted on the sidewalls too. As we can see, it does work. It has the same tire size, inflation pressure, and vertical loading, but now the sensors are mounted in the sidewalls as described previously in the second scenario, and of course with the updated boundary conditions. To further speed up the numerical analysis, we can design automations to post-process huge amount of FEA data. This is another example of how we can look at simulation data. As we can see, multiple variables can be considered when analyzing any dynamic loading scenario, starting from different stresses and strain components, and closely monitoring other output parameters like contact pressure in the footprint or footprint area. The same automations for post-processing of FEI data can be considered when analyzing the interaction between tire and sensor components and their impact on each other. Thus, we can optimize the position of the sensors in the tire so that the damage risk of both parts are mitigated. The structural analysis of the first sensor mounting scenario can be further supplemented by embedding other sensors like acceleration sensors and by analyzing their signal in real time. Thus, we can run very big DOEs and cover various load case scenarios to study the impact of dynamic parameter variations, any inflation pressure, tire loading, and speed, for instance, as well as any other parameters like tire slip angles or tire slip ratios can be considered. The structural analysis of the second sensor mounting scenario can be further supplemented by monitoring the elongation of the sensor's antennas. The same four loading scenarios results are presented here, and we take each spring elongation and monitor it in real time. So now a bold question arises. What if smart tires become super smart tires next? In a future case mobility context, which stands for connected, autonomous, shared and electric vehicles. Imagine having more than one data point from inside the generic TPMS sensor. This is where we introduce the virtual intelligent tire belt, which can be considered the next generation tire mounted sensor containing a cluster of 6 sensors for now. This virtual device aims to collect much more data about tires in real time. It could be connected to a TPMS sensor and contain 4 additional acceleration sensors to record more data from the tire crown and sidewalls. So the remaining question is now, is the mobility industry ready to investigate this new scenario? We are. In conclusion, smart tires are set to revolutionize the way we perceive and develop tires. New engineering requirements bring both challenges and opportunities for improvement. As said at the beginning, at Unleash Engineering, in partnership with GNS, we are developing capabilities for FEA pre- and post-processing of smart tires, and we are ready to support any smart tire development project with advanced 3D FEA tire model applications for beyond standard investigations. So if you are curious for a more extended demo, let's meet at the GNS booth for further discussions related to smart tires. Thank you.